So check this out. The hula hoop, she spun it ahead of time. So when it hit the floor, it is spinning. Right down here, there is skidding or slipping. So that means there's kinetic friction. So it's that kinetic friction that's causing the angular velocity of the hoop to slow, and at the same time, a force to the left is causing the linear velocity of the hoop to slow down and then begin moving back to the left. So a similar thing happens with the bowling ball. If you release it, at first it's not rolling, but it's sliding across the floor. And that kinetic friction creates a torque which causes the ball to begin to roll. And once the tangential velocity of the ball matches or is equal to the velocity of the center of mass, then the ball begins to roll and not slide. All right, here's our bowling ball. This is the force diagram of forces in the x direction. Yes, there's weight. Yes, there's a normal force, but I'm only interested in the forces in the x direction. So that's it. While the ball is sliding down the lane, it is the kinetic frictional force between the ball and the lane that produces a torque that causes the ball to begin to roll. Initially, when we release it, it is only moving with linear velocity. It's not spinning, but as it slides across the lane, this kinetic frictional force is going to produce a torque, which will cause it to begin to rotate in the clockwise direction. So part A of the question asks, once it is rolling and no longer sliding, what is the velocity of the center of mass in terms of omega, the angular velocity? Well, we know that VCOM is equal to V tangential when there is no sliding taking place. This negative sign here, if we look at our diagram and say that to the right is positive, then the velocity of the center of mass of the ball is to the right. But the tangential velocity here of the bottom of the ball is, since it's spinning clockwise, is to the left. So it's in the negative x direction. So VCOM is the opposite direction, but same magnitude as the tangential velocity of the ball when it's not sliding. And we know that VT is equal to R omega. So we replace VT with R omega and we come up with our equation that the velocity of the center of mass is equal to the negative R omega, where R is 11 centimeters. Okay, for parts B and C, while the ball is sliding, what is the linear acceleration and what is the angular acceleration of the ball? So here again, we see our force diagram. In the x direction, this is the only force. So my acceleration then, sum of the forces in the x equals mass times acceleration in the x. My frictional force, kinetic frictional force, is the only force in the x, and it's in the negative direction. We know that frictional force is mu times the normal force. The normal force is equal and opposite to the weight in this case, and the mu k is given to us in the problem as 0.21. So plug in 0.21 for mu. We notice m is on both sides. It cancels out. G is 9.8. Solve for acceleration. The ball will be slowing down linearly at 2.06 meters per second squared. Angularly, we know that alpha, the angular acceleration, is equal to torque over moment of inertia. The torque is produced by the kinetic frictional force, which acts at a moment arm distance or a lever arm distance of r, and it is producing a clockwise, the torque is acting in the clockwise direction, so it's negative. And then the moment of inertia for a solid sphere from table 10-2 is 2/5 mr squared. So plug in the numbers, the m's cancel, and we see that the angular acceleration of the ball is 46.8 radians per second squared in the clockwise direction. Okay, parts D, E, and F. Part D asks, how long does the ball slide? Part E, how far does the ball slide? And F, what is the linear speed of the ball when smooth rolling begins. Okay, so how long does the ball slide? Well, question is, when does the ball stop sliding? And we know that happens when the tangential velocity of the ball has the same magnitude as the center of mass's velocity. So I want to get both of these in terms of time, because that's what I'm interested in. How long does the ball slide? So I know that Vt is equal to r omega, and omega, if something starts from rest, is equal to alpha times time. The velocity at some later time is equal to the acceleration times the time duration that it's accelerating for. So I make that substitution there. Then the velocity of the center of mass, because the kinetic frictional force is a constant force, I know that the acceleration, the linear acceleration, is constant. So my equations of motion tell me that the velocity of the center of mass is equal to the initial velocity plus acceleration times time. So I'm going to set these two equal to each other because they were equal up here. So now this is equal to that. And the linear acceleration we figured out was negative 2.06. The angular acceleration we figured out was negative 46.8. The radius is 11 centimeters. Plug in the numbers and solve for t, and we see that the ball will slide for 1.2 seconds. Part E, how far does the ball slide? We figured out that it stopped sliding after 1.2 seconds. So the velocity of the center of mass, it initially was released from the bowler's hand at 8.5 meters per second. It accelerated linearly at 2.06 meters per second squared for 1.2 seconds. So I know that the velocity of the center of mass is 6.03 meters per second. Remember, the frictional force is a constant force. So that means during the time of sliding, the acceleration is constant. I'm able to use equations of motion in that case. So here's my equation of motion for distance sliding. It started off at 8.5 meters per second. The acceleration was negative 2.06. The time was 1.2 seconds. So there's my distance, and there's my velocity at time 1.2 seconds.